invite our speakers to come up and join our panel here. And the audience, please stand up and approach the microphone and ask questions.
Yes, this is my seat.
I guess so, yeah.
You have your name. It's there.
Please don't be shy. Come on over.
Squished under dryer. I'm gonna put my glasses.
Go right ahead.
Hi, my name is Fred Kwan. I'm an MD PhD student, actually part of the AI Cyanide group here. Thank you very much for the talks. The part that you had mentioned, Dr. Dreyer, was the normalization of data.
Yeah.
And as a researcher, I find that there is a lot of inherent bias when it goes into training these data sets that picks up on the confounded variables that's not clinically relevant. And I was wondering if the speakers could speak to some of the different techniques that go into normalization and what are available techniques that me as a researcher can use.
Well, I'll let the other guys speak too, but I'll just give you my perspective. And my concept of normalization kind of sits above modality specifically, but I'm sure Greg can dive in deeper about normalizing even at the modality level. One of the challenges, and you probably know this or others do from an AI standpoint, is even just are the significant bits on the left side or the right side of the data store inside a DICOM. So some of these things are pretty amazing how subtle differences in just data coming out of modalities is incredibly inconsistent, even inside of one institution. And so that in part was what I was speaking to by normalization, because it's a lot of lift that you would have to do if that could just be done for you. The other thing I would say is in doing models like, for example, breast density, one of the things we found in the principal components when you analyze the data itself is we were incredibly accurate at telling what the manufacturer's device was that made the thing, which is ridiculous. That just shouldn't have to be the case. And humans don't pick up on this, but that data is sitting inside of that data set. And so that's what I speak to about normalization. Currently, I think it's more of an art form than it is a science, because you just kind of have to go at it with a bunch of toolkits. The goal of AI Lab, though, or at least this effort from the ACR, we do a lot of this normalization with radiation dose, so it's just to expose the tools that we have for people to be able to use. I don't think it'll solve everything, but it's kind of an 80-20 kind of thing. Thanks.
Yeah, and I agree with that, and I think what we're really looking for is generalizable AI models. And so in order to do that, you need to expand the variety of the data that you use to train those models. One of the ways that we do that is with, or at least been proposed, is this federated learning, where we might move the model around and keep the data in the same spot. There's some really nice work done by Daniel Rubin at Stanford with Jayshree Kalpathy-Kramer from Harvard, simulating how you can do that. And Daniel Rubin's done some follow-up work as well, and it really shows that if you take a data set and you split it into multiple pieces, and then you try to do this federated learning, it works pretty well. But if you take disparate data from different institutions where they haven't thought in advance about how the data is labeled, haven't thought in advance about what the scanner mix is, it's a lot more difficult, a lot more challenging to do that kind of federated learning. So I think it's really still an open question as to how to solve those problems. I think they're easier to solve within one organization, but the data tends to be less diverse from the start. Then as you broaden out to multiple institutions, you really need to think about it in advance as a multi-institutional operation to make sure that you've got both the variety and the consistency.
I mean, I think the funny thing about your question is, like, it's like a really laborious human thing, but like once you start doing it, it's not really that hard. So it's like an ideal AI application, right? So what you would love to be able to is take the data right from the scanner and get it massaged into the form that you can use. I would say I'd agree with Keith that that's about 80% of the work, and it's not very sexy. But, you know, I think that that would be a wonderful area of research, especially when you could use such a tool for various institutions and take things with the minimal post-processing, because, you know, you need, when you do this federated learning, you need data scientists everywhere, and they all need to agree. And, you know, people often are not really great at agreeing with each other. So, you know, something that can, you know, do that automatically would be a wonderful project, I think.
I know there's other questions, but I'm just compelled to answer too, because what you guys said made me think of two other things. And one is, as Kurt said, it's not just important to normalize for training, it's important to normalize for inference. So a lot of reasons why these things break is because someone didn't make the model robust enough. But imagine if you did it the other way and say, well, I'll normalize all these different devices and make it look somewhat common. So now I don't have to put that burden on you, the manufacturer or the researcher that creates that model. So I think that's an important piece. The other one that I would say that I've seen in presenting, say, at MIT, it's interesting how when you're just pure data science and you're not sitting inside of a facility and you don't have control of the protocols, that they just say, well, all MR looks different. Well, but I'm sure Greg could modify the protocols to make sure that they're running appropriately for the AI that he knows is going to run. It's this kind of combination of the science of both sides of this that really lets you control some of those variables that otherwise are just out of control.
Why don't we take a question from that side?
Is this on? Oh,
Yep.
okay. Hi, I'm Angie. I'm an OBGYN and a postdoctoral informatics fellow. We mostly work with ultrasound, and I wanted to ask if you had any advice about working with ultrasound because it is more noisy than MRI, and maybe there was experience from other ultrasounds such as echocardiogram.
So I can tell you our experience. Number one, labels will give you fits. So if there's any kind of marking on the image, which there often is in ultrasound, removing that in a way that the machine learning algorithm doesn't still key on that to find the abnormality can be a challenge. If you're lucky, you have images that don't have burned-in annotations, and then you can start from there. One of the things that we found that's a great advantage from echocardiography standpoint is that the data there is very structured. They know what the computed or estimated cardiac output, ejection fraction, all that is, and so using that and trying to predict that, you have really nice, pristine labeled data set to start. I don't know that the low resolution really, AI, it'll take whatever information is there, so at least we haven't found it to be a particular challenge in that way. The other problem we found really interesting is we talk about ultrasound being user-dependent or operator-dependent, and you could imagine a less trained operator potentially being able to obtain good images because an AI algorithm can help to select the exact right plane for that user that's necessary to make whatever diagnosis is contemplated.
Yeah, I would say, so we've done work with Fuji around this topic, and I was kind of thinking it wasn't going to work very well, to be honest with you, just because ultrasound images are very difficult to interpret. They're very, different planes, trying to line them up right. I was actually amazed at how well AI algorithms were working on this. And I agree with Kurt that now you could imagine, because of point-of-care ultrasound POCUS that people can use, it can almost be like a stethoscope. And so now if you get it in the hand of an ER doc and there's trauma and you just say, there you go, there's no pneumothorax, well, that's pretty amazing. And that looks like that's not far into the future. So I think you'll see in your field, you could probably be getting a lot of assisted information during the time that you're scanning. Yeah.
Thank you.
So in many papers that I've been reading from the radiology field, machine learning researchers will look at some diagnostic challenge and just give some, let's say, accuracy at that diagnostic challenge, usually just using the imaging by itself. I wanted to hear the panel's thoughts on what a conversation might look like between computer and radiologist, or computer and another specialist, clinical specialist, where the computer, which has its own understanding of, let's say, an image, can work together with a clinician who might have other data about the patient to come to, let's say, a clinical decision. What does each need to know of the other?
What was the last thing, sir?
What does each need to know of the other?
Well, I mean, I think that's a great, that has been a limitation just because of the two groups have not crossed paths as much as they probably should. But
by the two groups here, I mean computer and clinician.
Human.
I'm thinking also sort of people who are more familiar with data science, computer science type side. I mean, it's like, these are all bits of information, right? And how do we integrate them together more effectively? I think it's challenging. I saw online a very nice video of like a radiologist's full day compressed into like 30 seconds. Yeah. And, what was remarkable was, how much time they spent looking at things besides the image. Yeah. And so clearly there's information there. Clearly that is the process of learning radiology. That's what we're teaching people currently. But, how do we bring that in so that, what looks like a normal study to me, if I didn't know the age, right? If somebody was an unmyelinated, child and I knew that they were under 2 years old, I wouldn't be too stressed out. But if you told me they were 6, I'd be really stressed out, right? The image is exactly the same. So, I mean, we can certainly, I mean, that's an extreme case, but we can certainly pull in more information in that way. And one of the things I'm interested in is how can we pull in that information to make better reconstructions? Because that's kind of a, kind of a bit of a foreign idea, right? Is you think the image is something that exists in space and it's independent of all that other stuff. But, images are there to be used. And how can we make them more useful if we include that into the reconstruction itself?
And I took your question a little different way in that we're doing some work to actually incorporate both types of data into what the AI is looking at. So the AI analyzes both data from the electronic record about the patient's history that the radiologist might be exposed to, as well as the images, and then coming to a kind of joint conclusion. And then I guess the other way to think about it is just the class activation maps and the other methods by which these algorithms can explain how they came to their conclusion, which can help the clinician decide whether or not to believe the advice.
Yeah, this is like, so here's how I interpreted your question. So there's two things, I think. One is exactly what Kurt said, is there's no reason why you shouldn't, if you know information, you shouldn't be able to give it to the model as you're building it. It gets a little trickier when you've got pixels and text and all of those things, but that doesn't mean it can't be done, and it should be done. And even like prior imaging, right? Why wouldn't you include all of that the human could? But then the second part of the question is, to me, this computer-human interface. And that's we are so new at this. And it's great, like the work that Greg does, as I see it, is he says, look, not much is going to change for the human. We're just going to give you better images or fused images or take image data that you don't have, but I'll simulate it and I'll give you all that information. And what that really does so elegantly is it makes it so that the human doesn't have to do much more than they did before. But imagine now if you're taking new data or data that somebody would actually draw by hand, and now you're giving the radiologist more data. How do you make it so they can use that as a tool to guide into what it is that they need to see to make a decision? I just don't think we're there yet. I mean, we've created models and say, oh, great, we can 99% at identifying spinal stenosis. Well, so what? How do you now put that in front of a radiologist so that they can do their job safer, faster, more efficient? And that's just a software challenge starting over again, defining the product and going at it. And my fear is, and I think this is real, is that you can't abstract that. You can't do that once for all of radiology. You do it once for this application, you do it again for this application, you do it again for this application. And so that just means it's going to take a long time, and hopefully a lot of people are doing this so somebody gets it right. Thanks.
I wanted to add a thought about that. I actually think that this is going to change the dynamic between the clinician and the radiologist down the road, and it may accelerate. Part of my life is living outside of radiology in the health information technology elements of a hospital, the EMR world. And I think this is going to force clinicians to provide the radiologists with more structured data, more specific information. And on the other end, it will probably be incumbent on the radiologist to take all our new knowledge and present it differently to the clinical staff as we move forward. That may be 5-10 years off, but I think it's probably what we should build into our thinking, that things don't need to stay exactly the same the way we practice medicine today, and things can be done more efficiently and better over time.
Let me say, you're going to be so sorry you asked the question.
No, I love these answers.
The other thing that's a challenge now, too, is forget about just the output of AI going to a human that has to make the decision. I agree with that. But what about the human that's now giving information back to that AI algorithm? So now we're starting to do this where we're actually, when we look at pleural effusion or pulmonary edema, put an arrow there. But now we're switching it to a bounding box. And then how do we draw that when it's a long tail? And how do we identify, is it the most proximal of those, or large, or size, or what vessel it's in? Can you really do that in the middle of someone dictating and trying to get their job done? But you could rapidly inform that algorithm to make it better. So there's going to be a lot of trade-offs, and we just got to figure all this out.
Hi, thanks. I'm Suresh Venkat, University of Utah. So Keith, you used some very powerful metaphors in your talk. You talked about data as oil, and you carried that metaphor through your talk. And you also talked about democratizing AI, which other speakers have talked about as well. So I teach an ethics class in data science, and we talk about data metaphors. In fact, we talk about the data as oil metaphor. What often happens is that we talk about data as oil to talk about refining it, to talk about mining it, to talk about selling it. We don't talk about data as oil as a fossil fuel, as something that actually has harmful consequences for how it's exploited, and how in fact other metaphors, like for example, data as personal property or data as public good, are other ways to think about what you do with the data. Also, when you talked about democratizing AI, I think my impression was it was the idea that you could have different organizations using the tools you build, and that way democratizing. But of course, democratizing means also to the level of the demos, so the people themselves who produce the data. So putting these two thoughts together, I guess I was wondering, in the vision you have for the Data Science Institute, to what extent do you see a future where, going back to the idea of wearables and people generating their own data, their own personal property, not oil, that they can be empowered using your tools to do the kind of initial filters, initial analysis on the data, to set off these warning signals, maybe you may be pre-diabetic, or the way Michael Snyder was talking about. And I'm curious whether that's part of the set of tools that you're thinking of building as part of the Data Science Institute.
Well, I tell you that I think that's a wonderful idea. I think it's the right direction to go to. And I think that, so imaging, unfortunately, sits inside of big facilities with millions of dollars of equipment that's, under procurement and security of, et cetera, et cetera. And so I think about as democratized as you can get in this country today is probably to give these tools to those people that are stewards of the data. But I completely agree with you that the individuals should be able to create tools off of their own data and be able to guide themselves as to what to do. That is a ideal goal to get to. And I take your first point. I don't like the oil analogy. Someone asked me to give a talk a month ago, and that was my title, so I thought I'll have fun with it. But I like it more as kind of a, not a fossil fuel, but more like as solar energy or something renewable, because I just think that there are a lot of ways where that analogy falls short. And I think there's a lot of things that when you think of the patient and you think of their information, it is pretty critical information way beyond the scope of a fossil fuel. So well taken. Thank you.
I mean, and just to add to that, I would think that, as we develop some of these techniques that make imaging easier to do, I think that we are likely to see people take more control over imaging themselves, much as kind of we're talking about sensor data. What can you wear that does imaging? Maybe these are places where you can go and get a check-in. There's certainly whole body MRI companies forming like rabbits out there. And we've had trouble with those kind of things in the past, dealing with things like false positives. I think that we're going to have to be very careful with them in the future. But I think that if you can start to make an MRI that can sit on a truck, and you don't need fancy hardware anymore, right? You can fix a lot of these things with software. So I think that there are definitely companies out there that recognize this, and the idea of taking imaging out of these mega centers like Mount Sinai and Stanford and putting them in more accessible places, making it easy, saying, here's a prescription, you can just go, once a month, you don't have to schedule anything on your own time, it takes 5 minutes. I think that then, if that can become the property of the person who is actually being acquired, they might very well want to pay for that and might get value out of it.
Yeah, I totally agree. I think ultrasound is going to be a good example of that. And here's just a thought experiment. When will the FDA release a low-cost ultrasound device for public use? And why wouldn't they? Because you might not really know what it's doing, and can it be doing something detrimental to you? Probably yes. How would they approve it if it was an AI decision that came out of those images and said yes, no, black, white, cancer, no cancer, mass, not, this, that, yes, no, and that was the output? Maybe it would be quicker to come out that way. And so if that's the case, AI might be guiding some of this kind of consumerism toward healthcare, which I would totally applaud.
It's also probably worth mentioning the NIH is rolling out their All of Us program, which is meant to stimulate patients contributing their data for research. And I think Kurt's well aware of efforts that the RSNA has supported. There's a reference implementation of an interoperability model working through patient portals to release the local radiology data when a patient chooses to contribute their data to NIH studies. So there are activities, again, to liberate data, so to speak.
Thank you.
Hi, so quick question. All three of you talked a little bit about the clinical implementation and challenges associated with this. So I was wondering if you guys could discuss one of those challenges, which is the FDA or the regulatory approval part. And my question's actually a little bit different, which is, do you think the FDA current approval process or 510(k) clearance process is actually a high enough hurdle? given the potential for harm, given, of course, an AI algorithm could harm thousands or millions of patients, whereas a human doing something wrong harms, significantly fewer. Thanks.
I'll take a stab at it. First, let me say my standard proviso of the FDA, I would not want to be the FDA at this time. It's incredibly difficult to do this. I think that these algorithms may be considered more like humans, where we do board certifications as opposed to devices, which never change. So trying to treat these like devices requires new guidelines and new standards. Does this fit into the old 510K? Does it fit into CAD? Does it fit into CAD X, E, T? Not really, right? So they're doing their best to try and take the tools they have to approve medical devices and make this work for that. But even the stress that they're having trying to describe how to do continuous learning and how to implement that safely is really a very daunting task. The other challenge is that these algorithms, like Kurt, when he showed the ability to use a chest x-ray or film picture on a phone, you make that available, and now you have 207 sovereign nations with their own ministries of health trying to figure out, is that okay or not okay? So this really democratizes some of the challenges around regulatory approval too. So to answer your question after that long preamble, I don't think it's perfect, but I think it's the best that there could be today. I think that we're all going to learn how to do this. The biggest challenge I have is that it's a high bar to get through, but it's a low bar that says this might not work at your facility. So yes, they've done the reader studies, they've done everything you have to get through that bar sometimes, but at the end of that, it's still, mileage may vary, and you have to test this out on-prem. That kind of begs for some kind of certification process beyond FDA.
I mean, that's really challenging, because what you're describing is you want to have very robust post-market evaluation, and the FDA, it's enough work to get through the first process, and then a much larger set of data, again with all the problems that the first person who asked a question all being different. How do you really take that in and know that it's actually hurting people, that you're actually going to take this very drastic step and pull something like that? I mean, is the staff there? I think it's very challenging, and I agree with the statement that everyone is learning about this together, and I think it's the best you can do.
Yeah, and I agree. I'll be brief because I tend to agree. I think the FDA has a very difficult job. I think that an approval or a clearance by the FDA does not necessarily mean that an algorithm is going to work in a given practice. So I think the main lesson is that if you're a practice that's considering adopting one of these algorithms, you really ought to examine how it works in your particular practice. And that's a very important step. It's really about those kinds of evaluation, benchmarking exercises that I think individual practices are going to need to do in some ways, or else the vendors are going to need to provide that as kind of a part of what they're selling. We'll show you that it works, and then we'll provide the algorithm for you, and perhaps update it over time.
Yeah, I mean, so take a device, take like a CT or an MR. It gets through FDA approval, and now it goes out in the wild. And one of the things the ACR did before my time at the ACR was to create this accreditation process, and it was because you could run that device wrong, or you could not update that device. And so even though it's a FDA-approved device, you're not using it appropriately, and so you're doing harm. And so what the FDA agreed to was an accreditation process where you have to, every 3 years, prove that you're actually using these things inside the intended use and scope. Could that look like what will be kind of the post-market surveillance process for algorithms? I think it's not an unreasonable approach. It's not too far off of what the FDA is comfortable with, and I think it solves some of the problems. So it might be, and it might, if that's the case, maybe even lower the burden of getting pre-market approval because you've got this post-market analysis going on.
But again, that's going to create a huge burden on radiology departments,
Right.
Because your CT scanners are a finite number, right? You can imagine, you showed your graph of all the possible use cases. That could easily be challenging, but it's definitely a way of thinking about it, at least for major applications or high risk applications.
Right. Thanks.
Hello, this is Zhixing from GGI's department of Mount Sinai. So I have a general question regarding the future of AI research. So the current ultimate goal of AI research is to build up a super powerful AI doctor that can replace your primary care doctor and specialist. even do a surgery for you. But so what is the current challenging to achieve that goal? Can the current machine learning framework achieve that goal if we have infinite computational power, like if we have quantum computing available, and we have huge amount of data, like every single patient, their EMR, epigenetic information is available for us. Thanks.
I'm not sure I agree with the premise of the question that, that we're trying to create that. I mean, what we're trying to do is to develop tools that help clinicians, radiologists, and others take better care of their patients, be accurate, make fewer errors, and that's application by application. I would say the closest that I could see something like that happening is in academics, we're made more efficient by the fact that we have residents and fellows, human trainees who help us with some aspects of the task. They collect some information about the patient, give us a quick summary. They preview the images and let us know what they think the salient findings are. They draft a report. I could imagine each of those tasks being something that an AI algorithm could do. So you could build a kind of e-resident, if you will, e-radiology resident for private practitioners who don't have the benefit of human trainees that would potentially make them more efficient and help them in many ways. But I think that even that is a stretch and could only be done for certain limited sets of problems where you can build AI algorithms. Let's say a chest x-ray. You know, you've got 14 common abnormalities, but you've got a long tail of 200 abnormalities that could happen on that chest x-ray. So even building just that for that one imaging modality would still be quite a bit of a challenge. So I think we're way far away to start thinking about it in those terms.
Yeah, I mean, I think it's what do you want to achieve, and then what are your tools to get there? And I think we're setting our sights, it seems like, for, as I said, like narrow AI, solving a specific problem, improving something, making it easier for a human, or maybe even for specific things, replace a human, possibly, diabetic retinopathy off a scope. But we're still just doing piece by piece by piece. And at the end, you know, maybe 100 algorithms, 1,000 algorithms later, you could start to get to where you want to. The other way to do it is to say, throw all the data in here, kind of take a Jeopardy approach and just hope I get 90%, which means I'm going to be better than the other person. But I just think fundamentally that we expect more of computers than we do of humans. We hold a higher bar, and so if there's an accident kind of, you know, off of a Tesla, it's different than if it's an accident off of a driver.
The other way to think of it is, you know, if there were workforce effects in radiology, where would they happen first? I would say probably in screening. You could imagine building an algorithm that was sensitive enough that if it said, look, this mammogram is normal, you know, we might get to a point where we'd say, all right, in some clinical settings, we're going to need fewer radiologists.
That was a very visionary, somewhat sci-fi question you put in front of us, but I would point out that if you go back to this morning's earlier session, if anything, it reinforced for me the complexity of human biology and really our level of ignorance at this point in time. And so if I think about the things I learned in medical school 30 some odd years ago, and how different it is today, and it's only getting deeper and more complex as we learn more and more about biology. So I think we've got a ways to go. Maybe during your career, some of that will materialize. All right, I think we have time for one last question behind you there.
So, till 1 year back, I used to be a community-based physician in India, and then I moved to New York to get trained in clinical informatics and AI applications in medicine. So what I am raising is something that my community colleagues ask me, and I'm not able to. Of course, I get away by saying that I'm a novice. I have just been trained for 1 year. But here we are fortunate to have people like this panel who are as distinguished as a panel can be in AI and medicine. The questions that I get are, one, about explainability, what we, in layman parlance, we call it black box problem. And the second question that I get from, again, community-based colleagues, not trained informaticians and trained AI clinicians, that how do we deal with legal liability angles when we decide something based on AI-driven. So the panel may not so much address the legal liability issues, but I was wondering if some light could be thrown on explainability. And this movement is also picking up a strength, what we call XAI and others.
Yep.
So could the panel take a moment to throw some light on explainable AI as we apply to medicine? Thank you.
Thank you.
Yeah, I wanted to jump on the explainable one and leave the legal ones for you guys. But,
Thank you.
but I mean, I think that a lot of work is being done. So, just to take a step back, what are these models? These models are typically large nonlinear systems with hundreds of thousands of variables, right? So at some level, your task of explaining, how decisions are made is incredibly challenging. And I think that a lot of the people here have done great work in terms of looking at saliency maps and things to, kind of just do reality checks as to whether something is making sense and perhaps keying off parts of the image that aren't actually relevant, things like that. But, I mean, I would almost take a step back in the more global perspective, which is, and this is a question I would raise to the audience, is if you have an algorithm that is working at better than human performance and you don't understand it, is it ethical not to use that? I think that's a really good question. And I just give you the example of lithium, which is a very common drug, actually the only drug that's been proven to reduce suicide in the setting of depression. And after many, many studies, many years, nobody knows what the mechanism of it is. And I don't think that anyone in this room would suggest taking that off of the pharmacy shelves. So I think that explainable AI is a nice to have, but I think that at some point, if we can have, performance that routinely exceeds what we can do otherwise, I think we have to think very deeply, is that something that we're willing to sacrifice to get better care of patients? And I realize that may be a minority view.
No, I actually agree with that. I think there, many medications we don't know the mechanism of action, and yet we use them because they've been proven in randomized trials. And so, that just to me indicates that we need similar kinds of validation experiments for these algorithms to show that they work. And if they do, we should adopt them. With respect to the medical legal, I'll take that on briefly because we had. At my prior institution, we implemented a different kind of decision support system. It was an order entry decision support. And we got some pushback from people who were worried about the medical legal implications of ignoring a pop-up or something of that nature. So if you look at the literature on this question, there are two papers that are interesting. One is there was a paper that described mock jury trials of decision support tools. It was an appendicitis application, surgery for appendicitis. And what they found was that the jurors didn't really care that much what book you read, what pop-up came up, what class you took, what the AI algorithm said. They cared, did you follow the standard of care after looking at all of the evidence and decision support and other information that was presented to you as a physician. So I'm not sure that there is that much greater a medical legal issue with these algorithms compared to the pop-up that does the drug-drug interactions, which we know is often ignored more than half the time in inpatient settings. So that's one side of it. And then the other side of it is there's a nice paper actually out of Partners where they self-insure for a lot of their malpractice, and they looked at hundreds, I think it was 400 to 500 claims over several years, and they looked at whether a decision support tool could have prevented the error that occurred that caused that claim. And they found that the majority of those claims could have been solved by decision support. So there's this sense that some of these algorithms actually could prevent some of the medical legal liabilities that are out there. So that's my perspective on those.
I would just add, just to get off the legal part, I would add that if you can explain AI, you should, right? And you should also explain when to use it and when not to use it. So there are times where these algorithms just fail, but sometimes they're not smart enough to know that they're failing. So it'll come back and say, this looks like pneumonia, but you put in a cat. So you need to actually add things like out of boundary, out of bounds, out of distribution errors into the inputs of these. And that's hopefully some of this normalization where I can say, look, this is an MR of the head. It's not a CT. It's not this. So you don't get these kind of stupid errors that come in. The other thing that I've seen, I was very encouraged by the concept of saliency maps, and then I got a little discouraged by them because they don't really, really, really tell you what it is that they're doing and why they're doing it. They're kind of just a gut check to say, looks like it's got, like kind of what Kurt showed, that, yeah, it's working on the joints, so it's probably doing, it's not shining over in the corner next to the patient name. But it doesn't necessarily explain everything you want. But back to Greg's point, if it doesn't, but it works, is that okay? Probably, but I think that we're just inquisitive enough as a species that we're going to dig and dig and dig and find these answers. So,
All right, well, thank you. I think we'll close the session with that. I'm concerned that Dr. Snyder's senses are all going to go off since it's getting a little bit past normal lunchtime here. But I wanted to thank our speakers who were terrific, and I hope you walk out of the room with a good notion of where radiology stands today in taking these tools and putting them to good use. So thank you, everybody. Thank you.